Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss lesson 3.1, which is all about how to actually write a lot of the chemical formulas and use molecular models in order to represent compounds. In chemistry, we use a lot of chemicals, and these chemicals oftentimes contain a lot of elements, creating a molecule. And it is often necessary to identify how these compounds are made up, the structure, whatever elements it present in that molecule or in that compound. So today, that's the whole lesson that we're going to do. And at the end of the lesson, what I want everyone be able to do is be able to represent these compounds using chemical formulas, structural formulas, and models. So let's begin by understanding who is accredited in creating a lot of these formulas and a lot of these names that we use or symbols that we use in identifying elements and compounds. His name is actually John Jacob Berzelius. He is a Swedish chemist, and he is the one that actually be able to identify a lot of the atomic weights of the elements, and he's the one who created the modern chemical symbol that we use in writing our chemical formulas. So, for example, if we are talking about hydrogen, we use H. If we are talking about gold, we use AU for its Latin name alums. If you're going to talk about copper, Cu. If you talk about sodium, we use Na. So he's the one who created these symbols that we use in notation. Notation is basically from the word note. It's how to write these elements and how to write these compounds. And this is very important because being able to identify the chemical formula of a compound, we can actually identify some of its properties. So if you know how the if you know the formula for the compound, and more importantly, if you know the structure and how that compound is made up of, you can actually identify a lot of its properties. And this is his picture. So today, what you're going to learn is the various types of formulas that we use when we are writing a bunch of compounds. So one of them is first molecular formulas, second empirical formulas, third structural formulas, which also has another version called the condensed structural formula. Another is a perspective drawing, which is very helpful in identifying the 3D structure of a compound. And we use a lot of various models like ball and stick model and the space filling model in drawing perspective drawings. So let's begin by understanding what are molecular formulas. Molecular formulas is basically showing the actual makeup of the compound. What do we mean by that is we are showing basically how many elements, how many of each various elements is are present in the makeup of the compound. This is very important because it identifies which element is present and how many of them. But what molecular formula does not show us is the structure and how the atoms, or basically the elements, and how they are put together, which is very important, like I've mentioned, because if we know how they are put together, we can show its structure and then we can identify a lot of its properties. However, even though we do not know how these elements or atoms are put together, we know the molecular makeup. So which tells us how many elements of each various elements is present in that compound. Another disadvantage of molecular formula is that it could be misleading because of isomers. If you remember what isomers are basically compounds that has the same number of elements on the another compound. It's just that they are put in a way that is different on the other element. So you can think of it is that they basically has the same element that makes them up. So for example, if you have a compound that has six hydrogen, six atoms, or six oxygen, and 6 carbons, so C6H6O6. So you know that's the molecular formula. You know how many atoms of each hydrogen, carbon, and oxygen is present, but how they were put together could be very different. They have the same numbers of all the elements, it's just that they were put differently from each other, and that's called an isomers. Since molecular formula does not show how they're put together, isomers could be misleading, but still molecular formulas is very useful as you can actually see a lot of the compounds that you would use in chemistry using molecular formulas. So here are some of the examples. Ethanol. Ethanol is a compound that has 6 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. Water, very familiar, or at least you guys should be very familiar. Know that the molecular formula of water it is H2O. What that means is that water composed or molecule of atom composed a 2 atoms of hydrogen and 1 atom of oxygen. And let's look at glucose. Glucose is a simple sugar that contains 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So what this basically is telling us is it's showing the actual makeup of the compound, what element is present in the compound or in the molecule, and how many elements is present in that molecule. So one molecule of water has 2 atoms of hydrogen and 1 atom of oxygen. Another example is hydrogen peroxide, the one that you use when you're cleaning wounds, and each molecule of hydrogen peroxide contains 2 atoms of hydrogen and 2 atoms of oxygen. So that's what molecular formula is. Now let's look at empirical formula. It has a relationship with molecular formula, albeit a little bit different. For empirical formula, what it's basically showing is the most basic form of the compound. I will show you what we mean by the most basic form later. But as the molecular formula, or like the molecular formula, empirical formula has its own disadvantages. One, it tells us very little about the compound, and also many formula can have the same empirical formula. So what does that mean? Let's look at the various examples. The empirical formula of ethanol is also C6H6O, very similar with molecular formula. So what is their difference? Let's go on. So you will see the difference in a bit. Same with water. Water also has the same empirical formula and molecular formula, H2O. But now let's look at glucose. The empirical formula of glucose is CH2O. So why is it very different? Because in empirical formula, we are using the most basic form. What that means is if you're looking at all the numbers present for each of the atom, what you want to do is find the least common denominator and basically divide that least common denominator to get the smallest number possible for each element. So for 6, 12, and 6, the least common denominator is basically 6. So 6 divided by 6, you get 1. 12 divided by 6, you get 2. And 6 divided by 6, you get 1. So for glucose, its empirical formula is CH2O. And let's look at hydrogen peroxide. By now, you should be able to know that the least common denominator between these two numbers, 2, is basically 2. So dividing both numbers by 2, you would get 1, which tells you that the empirical formula for hydrogen peroxide is basically HO. As you can see, it tells actually very little about the compound because it's just showing the most basic form. You don't even know how many of these elements or how many of these atoms is present in the molecule. So why is ethanol and water has the same molecular formula? Simply because this is the smallest value that is present in that molecule. So you have 661, least common denominator is basically 1. So 6 divided by 1 is 6, 6 divided by 1 is 6, 1 divided by 1 is 1. So you basically get the simplest, or this is the most simplest form of the ethanol, which is also its molecular formula, and which shows you how many carbons, hydrogens, and oxygen it has. So please do not confuse the two. As long as you can divide this to the most possible smallest number, which is 1, then you can do that. And that will give you the empirical formula, which basically shows you the ratio, or it can show you the ratio for each of the elements. So as for glucose, it has a ratio of, let's use my pen right here. So it has a ratio of 1 is to 2 is to 1. So for every, the ratio is telling you that for every one carbon, you would have one oxygen and two hydrogen. So if I have two carbons, it will tell you that I should have each of four hydrogen and two carbons. So that's basically what the empirical formula is. So they have uses, they have various uses for, but a lot of times we use the molecular formula because one, it shows how many elements do we have of each. Empirical formula has its uses, especially when we're talking about ratios. So that's two ways on how to write molecular formula of various compounds. Let's go on to the next part, which is a very interesting thing called the structural formula. From the name itself, you're actually showing the structure on how the atoms or the elements present in the compounds are put together. This is very useful because now you would see which atoms are single, double, or even triple bonded. Because in a covalent bond, in a molecular covalent bond, so it means there's a sharing of electrons between the elements. Sometimes singles, doubles, and even triple bonding happens. And structural formula is very useful in showing the bonds of various molecules or compounds. And like I mentioned earlier, this is very important because being able to identify the structure of a molecule or a compound will actually tell you a lot of its properties. Let's look at the various examples right here. So let's look at ethane. Okay, so ethane, uh, basically, if we look at the molecular formula, let's write the molecular formula for ethane. The molecular formula of ethane, from the picture here, it shows us that there should be two atoms of carbon and six atoms of oxygen. So that is the molecular formula for ethane. But let's look at the empirical formula. We should know that the empirical formula is the lowest possible number. So the empirical formula is CH3. Okay, so you can see that now. So how is it different? So the structural formula is showing you how the molecule is made up, or basically this, how they were put together. Since the molecular formula, which again shows you how many elements is present in each of the molecule, you have two carbons and six hydrogen. So if you have two carbons that are bonded together, which is denoted by the line here, and the hydrogen is basically bonded together in each of this carbon. So how to identify this bonding requires you to understand what we call the Lewis dot structure, and that would be actually that would be actually our next lesson. So for now, do not focus on how they're put together, but understand that this is what we mean when we talk about structural formula. In our next lesson, I will teach you on how to actually make this structure. So this is the Lewis dot structure, wherein it shows you how the sharing of electron happens. Okay, so another thing is, let's look at ethene. Ethene basically has a molecular formula of C2H4 and has an empirical formula of CH2. So, and here as you can see that there is a double bonding happening. You have a single bond, and then let's look at ethine, which has a triple bonding. So the structural formula is showing you how many bonding that is present in each of the atom and basically how they are bonded together. So I'm going to teach you how to do all of these in our next lesson, but just remember this is what we do in the structural formulas. Next, let's look at the condensed structural formula. It is related to structural formula, only we're condensing it. What do we mean by that is we are removing the dashes, we're removing the line. But you may get confused, but that means it's just this molecular formula. If we're just going to remove the line, it's basically the molecular formula. It's a little bit different because in condensed structural formula, you are focusing on the order of the atoms. So in structural formula, it shows you how they were built. So it's showing you how they were structured. In condensing them, what you want to do is be careful of the order of the atoms and how they were written. And what you're going to write them is in a single line. This is important because one, it saves you time. You do not need to identify a lot of the lines, which one goes to the second double, or which ones goes for the double bonding, which ones go for the triple bonding. And this is also, you can also use condensed formula when you are dealing with something called polyatomic, or when you have a group of atoms that are bonded in a single molecule. So later I will show you that, but this is an example of condensed structural formula. Let's look at ethane. Remember, the molecular formula for ethane is C2H6. This. So the structural formula of ethane is this part right here. But when we want to condense it, what we want to do is basically separate where the bonding happens. So for example, you have C here, and that C there, three hydrogen is bonded. So you have one, two, and three. So you have CH3, and then another C, and this second C has another 3H or 3 hydrogens bonded. So you ended up with having CH3, CH3. So this is the condensed formula for the structural formula of ethane. Now let's look at ethene. So for ethene, you have two carbons, and each of the carbon has two hydrogens. So you ended up having CH2 and CH2. Okay, so this is basically the condensed structural formula. So how is it different? How am I going to write this? For condensed structural formula, what we actually usually focus is the carbon. Because let's look at the acetic acid here. As you can see, you have two carbons. So we separate the acetic acids, the two carbons in the acetic acid. Our first carbon has three hydrogens. So you would have CH3. As for our second carbon, it has an O bonded to it, and it has another O bonded to it, and another H. So as you can see, you can write it as the C, it has two oxygen, so you have O2, and then it has an H to it. So what that means is this is grouped together, and this is grouped together. So if you look at acetonitrite, so you have two carbons, so you separate the carbons. The first carbon again has another three hydrogen in it, and our second carbon is connected to nitrogen, and it's triple bonded. So again, as you can see, there is order there. So you're looking at each of the carbon one at a time, and then yeah, you're looking at the carbon one at a time, and then you basically combine those two together. So that is the condensed structural formula. So you're just looking at the structure, break it down per carbon, and then basically write on the left side how many carbon or what elements is present in that carbon. Okay, so that is the structural and the condensed structural formula. Again, we're going to focus on how to write this in our next lesson, which is Lewis dot structure. Now let's go on our next part, which is the perspective drawing. In the structural formula, this is which was our previous number three structural formula. You're showing the structure itself. But as you can see, it is still flat because in real life, molecules are actually 3D. They're not flat, no, they are 3D. So 3D is another property that you want to identify in a lot of the molecules because now being able to identify not only the structure in 2D but the structure in 3D tells you so much more about its properties. And that's what we do in perspective drawing. We are trying to write the molecule or the compound in its 3D configuration. So we're focusing on 3D drawing now. But this time, we're not going to use a software that will allow us to create a 3D structure, but we're still going to use pen and paper. So how are we going to write a 3D or draw a 3D structure using pen and paper? It is very simple. It is still very similar with sorry, it says very similar with structural formula. You still uses lines, but this time we're adding what we call wedges and dashes. So here's some examples. So this is your Lewis structure, which is the structure that we talked about earlier. So we have one carbon, and bonded in that carbon is four hydrogen. But this is flat. This is just a basic structure. But what does it look like in real life? A 3D structure. Like I mentioned, what we're going to do is draw this in 3D by using what we call wedges and dashes. So this is your dashes right here. So this is your dashes. And this is what we call wedges. So how is this a 3D structure? Because dashes, it denotes that it is at the back, while the wedges denotes that it is something in the front. So what do we mean by that? So if you see something like this line right here, you can think of that as the flat. No, basically if you think about the paper, so the carbon is in the paper as well as these two hydrogen is in the paper. But the hydrogen here is behind the paper, while the H here is in front of the paper. So if we look at this sideways, you would see this is your C, this is your hydrogen, and you would have another hydrogen there. And then you would have the wedges here, which is another H, or dashes, sorry, and this you have another wedge that is the H. So if you're looking at this sideways, this is something that you would see. So, and then this is basically your paper that I was mentioning. So this is your paper, and then if you make it look at in front of it, this is sideways, and this is basically the front now. If you're looking at it in front, so this is basically the line of the paper, and then this is at the back of the paper, and this is at the front of the paper. So it's telling you basically the 3D structure of CH4, and CH4 is actually what we call methane. So that's what we use to identify the 3D configuration of a compound. We use wedges, which usually denotes it's at the back, and or dashes, which is at the back, and wedges, which is in the front. So here's another picture right here. So we have a methanol. So this is methane. This is a methanol right here. Methanol is a type of alcohol. So this O right here is bonded to oxygen and hydrogen here. And since they are using line here, this means this is in line with each other. So it's basically, you can think of this as flat. And the hydrogen is protruding in front of you, this hydrogen with a wedge, and this hydrogen is protruding at the back. So if I'm going to look at the perspective towards this side, what I'm going to see is something like this: COH, H, and then you have another H there, and at the back you would have H, and in the front you would have, just fix this. So for example, if I'm looking at this is what I'm going to see. Okay, so this is basically, again, this is all in line with each other. So if you see a line, they are all aligned. And the H, since it's a wedge, it's a front. And H, since it's a dash, it's on the back. So it tells you this is what we call the perspective drawing. Again, this is very important because identifying the 3D structure, the 3D configuration of a molecule will tell you so much more about its properties, which we're not going to discuss what properties they are, but when you go into college and pursue a higher degree in biology, especially molecular biology and chemistry, you would learn more about these properties present in a 3D structure. But this is high school chemistry, so we're not going to focus on those properties. And lastly, part of perspective drawing is what we call the ball and stick model. Basically, it's the same structure here, but only we're using balls and sticks. So it's a type of perspective drawing that still shows the 3D, only we're using spheres. And space filling model, it's basically the same with ball and stick model, only without the stick. It's all about balls. We're representing the elements with balls or spheres, and this is what it looked like right here. So these right here are carbons, this is oxygen, and these are H. So you can see, you can probably see now why is it called the ball and stick model, because you have a sphere and they're connected by a stick. And there's actually a chemistry set that, well, we sometimes use in chemistry to actually create this structure. It's a fun. It's like a Lego, but it's used in chemistry. It's all just a bunch of spheres and sticks that you can put together to create the element. So what is this right here? So you would have, so if I draw it in perspective drawing, it would look something like this. So you'd have C, H, C, O, H, double bonded with O, and then you would have a wedge hydrogen here, and at the back you have another H there. So what is the space filling model? It's basically this, but we're removing the sticks and we're just combining the spheres together. So you have your carbons there, you have another carbon, H, H, H. This is oxygen, and this is hydrogen. So that is example of the models that we use. So most of these are basically models. A lot of times you would use the molecular formula and a lot of Lewis's structure when you're beginning with chemistry. So these are some of the ways that we use when we are writing formulas and models to identify compounds. So our next lesson is basically I'm going to teach you how to use the Lewis structure and how to write various chemicals using the Lewis structure. So if you guys have any question about the lesson today, feel free to message me anytime, and may you guys have a great